Why does sodium bond with chlorine, while hydrogen bonds with another hydrogen? The answer lies in the outermost electrons. In this lesson, we'll see how valence electrons reveal an atom's valency and help predict the bonds it can form. Many atoms are reactive because their electron arrangement is not stable. To become more stable, they form bonds, often reaching an arrangement like the noble gases. The key question is, which electrons control this behavior? It's the outermost electrons, called valence electrons. They determine how atoms combine, whether by sharing or transferring electrons, and they prepare us for the octet and duplet rules. To understand valence electrons, picture the atom as a nucleus surrounded by energy levels, or shells. Electrons do not sit randomly. They fill shells in a fixed order, starting with the K shell closest to the nucleus, then L, M, and N as energy increases. Each shell has a maximum capacity. K holds 2 electrons, L holds 8, and M can hold up to 18. In many class 10 examples, we use simplified filling to focus on bonding and valency. This shell-by-shell distribution is called the electronic configuration. For example, 2, 8, 1 tells us how electrons are arranged across the shells. The valence shell is the atom's outer boundary. It is the outermost shell that contains electrons, so it is the path other atoms encounter first. The electrons in this shell are called valence electrons, and they are most involved in chemical reactions. Because of this, the number of valence electrons strongly influences how an atom bonds. Many atoms react by gaining, losing, or sharing electrons until the outer shell reaches a more stable arrangement. In short, valence electrons are the outer shell electrons that guide bonding. During reactions, these electrons may be lost, gained, or shared with another atom. That is why they help determine an element's reactivity and the kinds of compounds it can form. Elements in the same group of the periodic table often have the same number of valence electrons, so they tend to show similar chemical behavior. Valence electrons matter because they are the electrons atoms can actually use in bonding. Inner electrons are held tightly and usually stay out of the interaction. If the outer shell is incomplete, the atom may react to reach a more stable arrangement. Sodium becomes more stable by losing one valence electron. Chlorine becomes more stable by gaining one. That transfer creates ions, and the attraction between opposite charges forms an ionic bond. Nonmetals often reach stability by sharing electrons instead, forming covalent bonds. In a coordinate bond, the shared pair comes from one atom, but it still involves valence electrons. So, bonding is mainly a story of atoms rearranging outer electrons to reach lower energy and greater stability. Electronic configuration gives us a compact way to show where an atom's electrons are placed. Start with the atomic number, because in a neutral atom, it equals the total number of electrons. Sodium has atomic number 11, so we arrange 11 electrons. The first shell holds 2, so we write 2. The second shell holds 8, so we write 8. That accounts for 10 electrons. One electron remains, and it goes into the next shell. Sodium's configuration is 2, 8, 1. The final number is the key clue for bonding. Sodium has one valence electron. Valency is an atom's combining capacity, or its ability to join with other atoms and form compounds. Atoms bond because they tend to become more stable. To do this, they may lose, gain, or share electrons. Valency tells us how many electrons are involved in that process. Sodium commonly loses one electron, chlorine commonly gains one, and atoms like hydrogen and chlorine can share. Because valency is usually a whole number, it helps us write correct compound formulas. To find valency from electronic configuration, look only at the outermost shell. These valence electrons show how the atom can become stable. If an atom has 1, 2, or 3 valence electrons, it usually loses them, so its valency is 1, 2, or 3. Aluminium has the configuration 2, 8, 3, so it can lose 3 electrons and has valency 3. If an atom has 5, 6, or 7 valence electrons, it usually needs to complete 8, so we subtract from 8. Nitrogen has 5 valence electrons, so it needs 3 more, giving valency 3. With 4 valence electrons, atoms usually share, so the valency is commonly 4. Now apply the rule to water. Hydrogen has 1 electron in its outer shell, so its valency is 1. It needs 1 more electron to become stable. Oxygen has 6 valence electrons. Since 6 is more than 4, we use 8 minus 6, giving valency 2. So one oxygen atom can form 2 bonds, while each hydrogen forms 1 bond. That is why oxygen bonds with 2 hydrogen atoms, giving HO. Chlorine and carbon show 2 different ways atoms reach stability. Chlorine has the configuration 2, 8, 7, so it has 7 valence electrons. It needs just 1 more electron to complete its octet, giving it a valency of 1. That is why chlorine often forms 1 bond, such as in a chlorine molecule. Carbon, with configuration 2, 4, has 4 valence electrons. Instead of gaining or losing 4, it usually shares 4 electrons and forms 4 bonds. That is why carbon can make compounds like methane, CH. Let's pull the lesson together. Valence electrons are the outer shell electrons that control bonding. Valency tells us how many electrons an atom loses, gains, or shares to become stable. Electronic configuration helps us read that information quickly, shell by shell. Most atoms move toward an octet, while hydrogen and helium follow the duplet rule. As you move forward, keep asking, what does this atom need to reach a stable outer shell? That question unlocks bonding.